Now you know that in order to have secrecy, you need to share a secret code with someone. We have now our two friends that want to communicate secretly. Alice and Bob, they're there in blue, but they are at a distance. They are not in the same office, otherwise it's simple. You probably don't need much secrecy. They are very far from each other. And they want to communicate secret, but they have not shared yet the secret code. So how can they do it? You think that can use the mobile phone? No. If Bob calls Alice and they try to establish a secret code through mobile phone, you know mobile phones can be tapped. Many people, maybe not you and I, but other people with a few more means could learn what the secret code is, and the code is no longer secret. Now, so you see the devil that I have there would be very happy. Quantum physics allows solving this problem. So if Alice and Bob use quantum objects, that I will tell you later what they are, they can indeed establish a secret code by being separated from each other, by being in different locations, and in a way that no devil, no eavesdropper can learn about it. How does it work? What is a quantum object? Okay, the quantum objects that we use are particles of light, photons. Each photon can be sent from Alice to Bob, for instance, and carries some information. However, and here is where the quantum magic comes in, not all the information can be read. You need to know somehow how to read the information in order to retrieve it. If you ask the wrong question, the quantum system will give you a random answer, something that makes no sense. So you see now, Alice is sending these photons to Bob, and Bob somehow knows, well, there is a trick there that I don't have time to explain, knows how to measure them, because Alice and Bob are friends, they have agreed on something. Whereas the eavesdropper doesn't know how to measure them. So if the eavesdropper tries to measure, he simply messes up the whole communication. And Bob notices it. Bob notices that what was coming from Alice was not somehow what he was expecting. If Bob is receiving more or less what he was expecting, he knows that no eavesdropper was on the line. Now, this is one way of doing quantum cryptography. Here in CQT, we do it in a slightly different way. In this case, there are two photons. The source of these two photons is also in Alice's hands. Alice keeps one photon, sends the other to Bob. It's a very similar scheme. And these two photons are so-called entangled. In a sense, it becomes even more complicated for an eavesdropper to learn what happens there, because one of the properties of entangled pairs of photons is that each photon separately doesn't have well-defined properties. So for the eavesdropper, there is really nothing to learn there. Now, by measuring these photons, Alice and Bob can get zeros and ones, as we have them here, and these zeros and ones are private to them. The eavesdropper doesn't know them. So this is going to be their secret code. So how do you encode a secret message with zeros and ones? Well, you have to also, this becomes classical. No need of quantum physics anymore. You have also to write your message in binary form, in zeros and ones. As you know, for instance, in the ASCII code, all the letters of the alphabet are translated for computers into a sequence of zeros and ones. And once you have transcribed this message in terms of zeros and ones, you add bit by bit the message and your key. With the rule that, with a strange rule, binary calculation, 1 plus 1 is equal to 0 and not to 2, because you have only the possibility of saying 0 or 1. So 0 plus 0 is 0, 0 plus 1 and 1 plus 0 is 1, as you expect, but 1 plus 1 is also 0. And now you use these as a message that is a crypted message that is sent from Alice to Bob. Alice encrypts the message in this way, sends it to Bob. Bob has the key, has the secret code, he can decode it. The eavesdropper doesn't have the secret code, he cannot decode it.